Hey guys, so I just want to re-explain about graphing radicals when there are multiple transformations going on and it's a little hard to kind of visualize on a graph where you're going to move. Apart from making a t-table and just plugging in random x value to find the corresponding y value, you can also make a t-table by applying the transformations. So this might be a little bit easier, especially when the calculations are not as nice. Just remember that everything that gets applied to the x is inside a radical, and everything that is outside a radical gets applied to the y. So if we look at our parent function, the original 3 points that we have are 0, 0, 1, 1, 4, 2, and we're going to transform those. So we're going to transform those, and let's take a look at the transformation that's applied to the x. So x minus 5, I know I'm going to slide all my points to the right 5. So really, I'm taking all the x values and I'm adding 5 to it. So my new t-table for my new graph is going to be whatever my old x is from the previous table, add 5 to it. And then for the y, everything outside the radical gets applied to the y. And we do our reflections first, stretches, reflections, and then shifting. So we're going to multiply our y value by -1, so this is going to be -y, and add 2. Okay, so I'm going to take 0, 0, 0 plus 5 is 5, -0 plus 2 is 2, so 5, 2 is 1 point, 1 plus 5 is 6, -1 plus 2 is 1, 4 plus 5 is 9, -2 plus 2 is 0, 5, 2, 6, 1, 9, 0. And those are the exact same points that you get if you pick x values in to get the corresponding y values. And that way you might, when you do that, you might have to think, okay, what x would I put into the function that would give me a nice y value? You might have to do a little bit of thinking, whereas if you just use this table and just transfer it to the next table using the transformations, it might be a little bit easier. Okay, so let's see if the next one works the same way. I'm going to have my original table of my original function, xy, at 0, 0, 1, 1, 4, 2. That's my parent function. Okay, and then applying the transformations, let's look at what transformations are applied. So to my x, I'm going to -2, slide 2 to the left because it's counterintuitive. And to the y, all I'm doing is multiplying the y by 2. Okay, so my new table, 0, 0 is going to become -2, 0. That's my new vertex. And then, and you can identify the vertex because it's in vertex 1. The vertex is -2, 0. And then for x, 1, 1, 1 minus 2 is -1. And 1 times 2 is 2, -1, 2. And then 4 minus 2 is 2, 2 times 2 is 4. And you have your 3 points, -2, 0. -1, 2, and 2, 4. And that's the same graph that we got. And so when we get to the cubics, when it gets harder, then it might be helpful to do the table. So we take our original parent function, y equals the cube root of x, and we pick a few points. So we know that when x is 0, it is 0. When x is 1, it's 1. When x is 8, it is 2. Similarly, when x is -1, cube root of -1 is -1, and cube root of -8 is -2. So we can take all of these points and apply the same transformation. So we look at everything inside a radical gets applied to the x, so all I'm doing is taking all my x coordinates and I'm sliding to the left 7, so x minus 7. Your horizontal and vertical transformations do not affect each other, so it doesn't really matter which one you do first. x minus 7. And then for your y, looks like I have to multiply the y by negative 3 and then subtract 6. Multiplying the y by negative 3, that's going to be your stretch and your reflection. And then I'm going to slide down 6, so minus 6. Okay, so then doing that, that's going to give me negative 8 minus 7, that's your negative 15, and that's what we got in class. Negative 3 times negative 2 is 6, minus 6 is 0. Negative 1 minus 7, that's going to give me negative 8. Negative 3 times negative 1 is 3. 3 minus 6 is going to give me negative 3. And then 0, you can look at 0, 0. 0 minus 7 is negative 7, negative 6. 0, 0 got slide 7 left and down 6 because the reflections and the stretches don't apply to 0, 0 because that doesn't change anything. So 1 minus 7 is going to give us negative 6. And 1 times negative 3 is negative 3, minus 6 is negative 9, 8 minus 7 is 1, negative 3 times 2 is negative 6, minus 6 is negative 12. And so we have a few more points in between the negative 15, 0 and the 1, negative 12 that we got in class. So negative 7, negative 7, 6, and now because I have a few more points, maybe I could scale by 2s now. So I'm gonna scale by 2, 4, 6. So negative 7, negative 6, here it is. And then I can graph negative 8, negative 3. And I can graph negative 6, negative 9. Okay, and then negative 15, 0. So a better graph. Okay, and if you scale by 3s, then you get a few more points in between. And that's it. So it might be this way, applying the transformations to your original table might be a little bit easier than trying to figure out, all right, what x can I put in that will give me a nice y value. It's just another way of doing it.